Hello everyone, this talk title is on synchronization of generic lithography machine open chains using a novel fine positioning stage system. The authors are Yazan Arawashdi and Mohammed Al-Janaidi, both from Memorial University in Canada, and Marcel Hertze from Eindhoven University of Technology and ASML in the Netherlands. In this presentation, we start by outlining a low-fidelity dynamical model of a generic lithography machine and the assumptions made, followed by the adapted modeling perspective, whose benefit in capturing the energy flow and the interaction of the chain in the machine is then highlighted. Next, we briefly present the proposed fine positioning stage generic model and assess its impact when it is added to an existing machine. Having the machine model and the fine stage being introduced, we then use the available information to formulate the chain's synchronization error and write it in a way that suits the fine positioning stage. Later, the benefit of using this error in enhancing the machine performance and the throughput is looked at. We end this talk by stating some concluding remarks. To be able to deal with this costly and sophisticated machine, an equivalent lumped mass spring damper model is used to capture its motion. Focusing on the positioning stages and excluding the handlers, illuminator, immersion or cooling hood, it's possible to deal with a typical lithography machine as a machine that consists of 3 open loop chains. Light beams pass through the pattern managed by the reticle chain to the substrate in the wafer chain after being magnified through the optics chain. Due to the rapid production requirements, various positioning errors take place in the lithography process due to the needed aggressive motion profiles. While studying these errors, the built machine model helps in assessing its performance and the effectiveness of the proposed fine stage in mitigating positioning errors. The motion of the 3 end effectors, namely the mask, the lens element, and the die, must be synchronized during the scanning process. In this study, the synchronization between the 3 end effectors is investigated. The adapted perspective of tree-like topology helps in capturing the energy flow throughout the machine. This requires understanding the relation between motion-related and anti-vibration control signals. For example, if the anti-vibration wrench, denoted here by W1, is applied correctly as shown in the figure to the right, then the machine frame will strictly function as an energy sink and therefore vibration will not propagate among chains. Consequently, the motion-related signals can be designed independently. In case W1 is absent, maybe as depicted in the figure to the left, then vibration can propagate to other chains and deteriorate the machine performance unless the machine-related signals are cooperatively designed. Therefore, a stage positioning loop should oversee its affecting disturbances originated at any place within the machine. The reticle chain consists of 3 stages, the long and the short strokes and the reticle stage, except for the latter as being an unmotion-related subsystem. Having dual motion-related stages allows having an extensive range of motion with high positioning accuracy. For simplicity, we approximate these stages using an uncollocated double mass spring damper system. If desired, flexible modes can be included by adding more mass spring damper systems in cascade. However, this will increase the model complexity. Adapting a dual stage structure in a chain, the large range micron scale movements are accomplished by the long stroke stage using commuting actuators capable of strokes up to 1 meter. The small range nanoscale dynamic tracking and positioning are conducted by the short stroke stage using Lawrence actuators, for example, with a stroke of up to 1 millimeter. As a result, the stage can cover a large range with high positioning accuracy. Within the reticle chain, the proposed fine stage may completely replace or upgrade the short stroke as depicted in the figure at the lower right. In this study, the fine stage is realized using a flexural mechanism and a multitude of piezoelectric actuators as depicted in the figure at the top right position. Hence the name Smart Material Board Regulator, or Smbr for short. The remaining figure shows the used model of the reticle chain. Compared to the reticle chain, the wafer chain is heavier and moves at quarter speed due to lens magnification. Also, the wafer chain covers motion in the XY plane while the reticle chain moves only along the Y direction during the scanning phase. A dual stage structure is adopted at this stage as well, allowing the wafer stage to cover a large range with high positioning accuracy. It's noteworthy that the wafer stage has 6 degrees of freedom and therefore is capable of realizing in-plane motion in the X, Y, theta, Z directions, and out-of-plane motion along Z, theta X, theta Y directions. The in-plane motion takes place during still and scan portions of the lithography process, while the out-of-plane motion maintains focusing and leveling of the wafer during that process. Both the in-plane and the out-of-the-plane motions are coupled. Therefore, 6 degrees of freedom analysis must be carried out. The optics box usually utilizes active optical elements such as motion-controlled mirrors with a suitable control and measurement system to realize an adaptive optics system. In this study, for the aim of simplicity, the optics elements of the optics box have been approximated as a single lens element, specifically the last lens element in deep ultraviolet machines, that is called with exchangeable last lens element. It's also assumed that all the stages in this chain are non-motion related systems. Moreover, more complicated models can be obtained by considering each individual lens element. This can be achieved by assigning a fixed body frame at each lens element. The inertial quantities of any stage within any chain can be captured in a recursive form using algorithms. This is obvious from the shown position, velocity, and acceleration kinematic quantities that are given here in recursive forms. The same applies to the mass and inertia quantities. According to this figure, each chain in the machine consists of a number of stages whose body fixed frames are attached to the center of gravity of their corresponding stages. Defining a suitable generalized coordinate system, both the linear and rotational motion of a chain can be obtained. In a matrix format, the overall three-dimensional chain dynamics, including both the linear and angular motions, can be expressed as shown here. Using the right dimensions, the dynamics of the three chains can be obtained. Aggregating these models along with the frame dynamics, the three-dimensional machine state space model can be obtained as given here. This machine model can be treated as linear parameter varying when the values of the angular motion are available. Now, various time domain studies can be conducted at the machine level. Under step and scan trajectories, in-plane, out-of-plane, and synchronization errors may arise. The proposed stages should be able to manage at least some of them. The fine stage or Smbr improves the reticle stage and provides additional degrees of freedom. Based on the model fidelity level looked for and the assumed range of operation, associated nanopositional nonlinearities can be included or excluded. In this study, we only included the linear range of operation of the involved actuators based on the developed low-fidelity model of the lithography machine. Adopting linear Lambda spring number approximation, a generic Smbr model can be introduced and tuned such that the needed design requirements are identified under desired performance metrics. In the Smbr design process, we repeatedly addressed the following questions: how many piezoelectric actuators to use? What is the best geometric distribution of actuators? And what are the design requirements, namely the mass, the stiffness, and the working space? In this study, a pre-designed Smbr that meets the desired performance metrics was used. As shown in these figures, The fine stage improves the reticle stage tracking and synchronization capabilities. The synchronization error was evaluated for two identical hypothetical lithography machines, where one of them has the Smbr as a replacement of the reticle stage. The proposed Smbr guarantees better performance during the step and scan phases. The machine performance under the Smbr, driven by the mask die synchronization error, is superior to that obtained when driving the Smbr using the reticle chain tracking error. This motivates us to look into the results obtained when driving the Smbr using mask lens die synchronization error. Since the operating principle of a lithography machine requires the interaction between the reticle, lens, and wafer chains during the scanning motion, it's imperative to find a mathematical model for such an interaction. This model helps in understanding the errors propagation that affects the machine yield. This can be done by tracing the light ray that passes through the reticle to the wafer through the lens. Both the overlay and contrast measures are important specifications in lithography machines. The overlay is defined as the ability of the lithography machine to expose two images on top of each other. The overlay is affected by the lower frequency part of the positioning errors of the stages during exposure, and it can be measured using the moving average, or for short known as MA. The contrast is characterized by the moving standard deviation, or for short known as MSD, of the higher frequency part of the positioning errors during exposure in the y direction. The focus error due to lens heating and wafer unflatness is another source of error that primarily takes place in the Z direction. In this study, we focus only on the first two errors and derive the full and partial synchronization errors in the XY plane when the chains are perfectly parallel to each other. The mathematical expressions of partial and full synchronization errors are shown here. As shown in these figures, using all position information from the reticle optics and wafer chains under full synchronization results in a better MA and MSD machine performance compared to the case when partial synchronization is used even during the stepping phase. Therefore, full synchronization guarantees machine performance during all operation phases. Having these satisfying results, it's important to check that the needed Smbr reference signals under both types of synchronizations and the given machine operating conditions are attainable. Indeed, based on these two figures, the working space limits of plus minus 11.7 micrometers are not violated. This motivates us to investigate whether the fine stage utilization under chain synchronization can in fact increase the machine throughput or not. In a try to increase the machine throughput under the proposed Smbr and full chain synchronization, we found that it's possible to optimize the step and scan trajectories such that the operation time is reduced while maintaining the desired machine performance as shown in the figure. The optimization was done while the machine and Smbr parameters are both kept unchanged. This shows the potential of having the Smbr as an add-on to existing lithography machines. In conclusion, this study covered a generic state space lithography machine dynamical model that helped in capturing energy flow within the machine and chains dynamical interaction. Moreover, this model helps in capturing the design requirements of the proposed final stage that is used to enhance the machine performance and throughput through the utilization of partial and full chain synchronization errors. Finally, being a suitable add-on, the proposed fine stage can be used to upgrade an existing lithography machine at a lower cost. Thank you.